Hey guys, today we'll be talking about the physics of a falling object. Here's our fundamental principle. It's Newton's second law. V final equals V initial plus F net over m times delta t. It's our fundamental principle that we will be working with primarily in this video lab. So what were we trying to do? Well, we're trying to capture a tennis ball falling in real life, upload the tennis ball video into Tracker and extrapolate useful data, use a computer model with Newton's second law, and try to model the real life motion of the tennis ball using VPython. We will also discuss terminal velocity in the context of this lab as well. So what happened? Well, in this scenario, the two models that were created were essentially the same in the prediction of the motion of the tennis ball. Both models underpredicted where the tennis ball should have been in real life. So here's our setup. You just need a tennis ball, a person, and a camera. You just need to capture the motion of the tennis ball falling from a specific height from rest and upload that video into Tracker. Here's my Tracker data, or Tracker video. Notice that the origin of the axis is at the ball, with the negative y direction being down. The time frame being considered is roughly half a second. Here's our observed model data, with our position versus time of the observed tennis ball. Now let's try to model that motion. We're going to see if we can model that motion of the ball using VPython and computer code. So what do we need? Well, we're going to go back to our fundamental principle, or Newton's second law. We need to consider F net, which is super important, mass, and mass. Notice that the initial velocity is the zero vector because the ball is initially dropped from rest. Really important, just keep that in mind. Now let's consider only gravity. Let's assume for this model that gravity is the only force acting on the ball. F equals negative mg, and F net is the weight force. We'll focus more on F net here rather than the idea of updating velocity and position. Those two are just fundamental principle rewritten in VPython code, and which we basically did in our first lab video. So here's our Python code for gravity only. These are simply just the initial conditions needed to start the code. Notice that our g constant is 9.8, and the mass of our ball is 0.057 kilograms. F net is the only force of gravity. So, according to the code we've written, it's exactly that. F net is only the force of gravity. Here's our gravity only model. Position versus time. Now let's add drag. What changes in the model with drag being considered? Well, F net is now the weight force plus the drag force. The drag force is b, some constant b, times velocity vector squared. We now have a constant b, which is the constant that is found empirically using the data we observed. By guessing and checking into the final position of the model is equal to the final position observed, or as close as possible. And again, here we'll focus more on F net. Here's the initialization of gravity and drag. The exact same thing, but now we have the constant b. Same thing again as our gravity model, but instead here we add the drag force to the F net and we model the drag force in VPython code. Here's our gravity and drag model with position versus time. Now here's a comparison of all three models. So, well, the models didn't do a perfect job. Gravity only model was underneath the gravity and drag model. But why? The blurriness of the camera and the ball makes inaccurate true observations of the data, or perhaps drag played much less of a role as a force acting on the ball, because the time frame being considered was only half a second. Let's talk about terminal velocity, defined as when the drag force on an object is equal to the force of gravity on an object, or more intuitively, when the velocity of the ball is constant while the ball is traveling through the air. This is because the pushes and pulls acting on an object equals zero, giving constant velocity, and thus terminal velocity. Can the models predict terminal velocity? Well, let's think for a second. In order to achieve constant velocity, and therefore terminal velocity, net force must equal zero. In which model is this possible? Gravity and drag model. The gravity and drag model is the only model of our two that is able to predict terminal velocity. F net can equal zero in the gravity and drag model because drag acts in the opposite direction of gravity in this case. The gravity model cannot predict terminal velocity. F net will never be zero with just the force of gravity. But what if? So let's take into this hypothetical situation with terminal velocity. What if the ball was thrown downward? Well, if given an initial velocity, the ball would reach terminal velocity more quickly. Using the gravity and drag model, if we give the ball an initial velocity of 2 meters per second downwards, we see this model. We see that the graph straightens out relatively quickly and has a constant slope and therefore a constant velocity. The parts of the graph where the slope is linear is where the ball has reached terminal velocity. Why? If the ball is thrown with the initial velocity of 2 meters per second, then the ball interacts with the drag force more quickly. Drag force is proportional to the velocity of the ball. One more time, terminal velocity is reached where the magnitude of the drag force equals the downward force of gravity. Science. Alright, thanks guys for watching my video. Shout out to all those who watched it, and thank you for your time.